one of the remark, and then we'll move to the double and triple integral. So in Lagrange multiplier method, we discuss the function of three variables f of x, y, z. We want to maximize or minimize subject to the condition g of x, y, z is equals to 0. So here we have maximize or minimize the function subject to single condition g of x, y, z equals to 0. But for example, if we have instead of one condition, suppose we have two functions g1 and g2 which equals to 0. So then there is a method, just small modification is required. So let us just write down the formula. So this is basically Lagrange multiplier method. Subject to two constraints in three variables. So here we want to maximize or minimize the function of three variables subject to the two equations. So these equations are represented by two functions g1 and g2. Right. So we want to maximize or minimize the function f subject to these two constraints. So the first constraint is g1 of xyz is equals to 0. The second constraint is g2 of xyz is 0. So in this case, to solve, to apply this method, first we check the gradient condition. So we need the condition. So here there are two gradients. So gradient condition will be gradient of g1 should be not 0 on the first equation. And the second condition also needs second equation also need to satisfy for the gradient condition. So gradient of g2 is also non-zero on the all points x1, y1, z1 satisfying the second function, that is g2 of x1, y1, z1 should be 0. So all points on this surface the gradient should be non-zero. So if these two conditions are satisfied, then we can apply the Lagrange multiplier, and after that we solve the following equations. So for the first constraint, for the earlier method we were checking gradient of f equals to lambda times gradient of g, right, for the single equation g. But now we have two equations. So what we will check is we will check gradient of f equals to lambda times gradient of g1 plus mu times gradient of g2. And instead of single condition, now we will take the two conditions. So both of the equations we will consider. Right. So totally, basically we get five equations, and there are two indeterminates, lambda and mu. Right. Earlier there was only one lambda was involved in this method. So this is just a method which we explained whenever we have two equations. So we'll find out all the possible points x, y, z satisfying these equations, and then we find the value of the function at all those points. So example I will not discuss today. One example is there in the tutorial. So tomorrow it will be discussed during the tutorial session. So today what we want to discuss is double and triple integral. So let us start with double integrals. So what is double integral? So double integral means we have a function of three variables, a function of two variables, f of x, y. So graph of the function will be basically z equals to f of x, y, and such a function we want to integrate over the region given in the xy plane. So this is x-axis, y-axis, and z-axis. So we want to integrate this function which is in the xyz plane, essentially above the xy plane, and over a particular region in the xy plane. So this is region R in the xy plane. So if we integrate this function over this region, we get the all the points up to the function. So that basically is this portion, right? So it is kind of a shadow, you can kind of shadow in xy plane. That is basically the region, right? So whenever we have a function in xy plane, y equal to fx, and we integrate that function, what we get is area. But here what we get is essentially we get volume. Let us write down these as of in words. So the integral of the function f of xy over a region R in the xy plane is the volume. So volume we usually represent by V, and that is nothing but now we have two variables over which we are integrating. So we write double integral over the region, and we represent it by d of a. So d of a is basically the small area of portion of the region. So whenever we have a closed interval AB, and we integrate the function f over that, what we do is we divide the interval in small subintervals in one variable case. So similarly here, what we have to do is we have kind of two intervals, right, which bounds the region, and then we divide these two intervals into subintervals in on x-axis and y-axis. So that means our region is divided into small portions. So this small portion changes this difference of small portion of the region, area portion basically of the region R. So therefore, such an integral is known as kind of area integral, or integral over area of the region, and it represents the volume of the function over R. So how to find such a volume? So it depends on what region is given and what function is given. So depending on function and region, there are some cases essentially on the region, how it looks like. So first theorem we will study is Fubini's theorem. So that is whenever we have a region as a rectangle. So let us write down the theorem. So if we are given a function f of xy, which is a continuous function, so we will not use much of Riemann integration in this chapter. We mostly use the usual integral, and therefore we usually will take the functions which are continuous. So particularly for the double and triple integrals. So suppose we have a rectangular region R, which is uh, which is given by all the points x, y, such that a less than equals to x less than equals to b and c less than equals to y less than equals to d. Right. So that means x is in the closed interval ab, y is in the closed interval cd. Then this volume, which is integration of the function, can be found by directly integrating the function first with respect to x and then with respect to y, right? And whenever we have a rectangular integral, we can switch dx and dy. So that means what? That means we can write this integral as a integral a to b first, c to d afterwards. So integrating first with respect to y and then with respect to x. So we have interchanged dx and dy, and that is possible only when our region is a rectangular region. So let us see some example when we can actually verify these. So calculate or find the double integral. So whenever our x is between 0 to 2 and our y variable is between -1 and 1. and our function is 100 minus 6x square y d of a. So because of the Fubini's theorem, we need to find only one integral, either this integral or this integral, right? To evaluate this example. But for the sake of verification of Fubini's theorem, let us find both the integrals. So note that the integral 0 to 2 cross minus 1 to 1 of the function. So if we integrate using the first formula, that is first integrating with respect to x and then with integrating with respect to y, what we will get is we will get the limit of the function x is 0 to 2 and the second limit, which is limit of y, is minus 1 to 1 of the function dy dx. So integration, all these things we already know. So just let us integrate this function with respect to y. So this integration is something like partial derivatives, right? So here we are integrating the function partially with respect to y. So whenever we integrate function partially with respect to y, our x variable is constant. So that means when we integrate this function with respect to y, we get 100y minus 6x square y square divided by 2. And y 6 by 2 is basically 3. And the limit is y is equals to minus 1 to 1. Right? So whenever we substitute these values, we can see that the function will become 100 minus 3x square minus minus 100 minus
एक्सक्यूज मी
3x.
सर
Yes.
सर इसके अंदर ये जो 0,2 और -1 और 1 लिखा है तो हमारा x जैसे a टू b में होता है तो हमारा a यहाँ पे 0 होगा और b -1 होगा ना या फिर
No, no,
मतलब
this is
हमने a
the
b
first
को
the first
साथ में लिखा
interval. Yeah. So the first interval is a cross b. Yeah. So what does this mean? This means x is in a to b, y is in c to d. So that means what is our region? Our region is basically AB cross CD.
ओके सर ओके
So that is what is given in the question, the region. So this is essentially the region, and using the region we have found the limit of x and y here. We substituted, and, uh, and then we have integrated with respect to y. So now finally the integral will become 0 to 2 200 dx, and that is nothing but 400. Yeah, so here we can apply those uh, uh, the results of the integral regarding odd function and even function. So basically 3x square is cancelling because it is a even function. Right, this is a even function of y. So anyway, these two terms will cancel basically. Okay. So, so, so this is one direction that we have first integrated with respect to y, secondly with respect to x. Now, on the other hand, if we integrate the function first with respect to x, then what we get is, on the other hand, so here we basically apply the Fubini's theorem. So using Fubini's theorem, so when we apply Fubini's theorem, we can write the first integral as in this form. Alright. So that is exactly the Fubini's theorem, that this integral we can write as either this form or this form. So this one we used earlier. Now we will compute the integral using the second formula. So in that case, we can easily verify this part also. That on the other hand, double integral 0 to 2 cross 1 1 minus 1 1 of the function is nothing but integral minus 1 to 1 0 to 2 100 minus 6x square y dx dy. So first we integrate with respect to x now. So then we'll get integral minus 1 to 1 100x minus 2x cube y. The limit is of x is from 0 to 2 dy, and this is nothing but integral minus 1 to 1 200 minus 16y dy, which is equals to 200y minus 8y square. The limit is from y equals to minus 1 to 1. So once again, this 8y square is a even function, so that term will become 0, and finally we get 400. So it doesn't matter first we integrate with respect to x or is with respect to y, the answer we are getting is same, that is 400. But this is actually true for the rectangular region only. In general, this may not be true. So what do we mean by uh, by in general? So let us see the general Fubini's theorem. So that is general version of stronger version. So here essentially the region is not a rectangular region. So what does that mean? So that means that we have a xy plane in which our region lies. So whenever region is given, and it is a kind of smooth curve. So smooth here means basically there are not many angles. So such a curve we can always divide into two parts. So for example, I restrict this between two different values of x. So this is basically x equals to a line. This is x equals to b line. Then along the y-axis, we can divide this curve into two parts using these two lines. So first, we will get this curve, right? So that is between the line x equals to a and x equals to b. So this curve we can say y equals to g2x, right? Y is a function of x, and on the other hand, the below curve which we are getting, that curve from a to b, so that we will denote by y is equals to g1x. So essentially, I have written g1 below because essentially what is happening is we are dividing the region along the y-axis. So on y-axis, we should go from negative numbers to positive numbers. Therefore, it will go below to above. Alright, so this is kind of uh, dividing the region along y-axis. So suppose we want to uh, divide the region along x-axis. So then what happens? Let us see that. So again, we have a same region. Right, this is the same region R, which we want to divide along x-axis. So here what we have done is we have found two constant values of x, but now what we will do is we will find two constant values of y. So what we have is we have y is equals to t line, to we have y equals to t line, and what we shall do is we shall divide the curve between these two lines. So one curve we will get is this one, right? So now this is, earlier we have written y as a function of x, but now we will write x as a function of y. And on the other hand, we get another curve up to this point, and that curve we will write as x equals to h2 of y. Right. So sometimes depending on what is uh, the question or what is the region, we need to choose the function y as a function of x or x as a function of y, and therefore we can divide the given region in either of these form. So first form we can say it is kind of type 1 for simplicity, and second one, let us say we can say it type 2. So whenever we say type 1 region, that means we will write y as a function of x, we bound the region as y as a function of x, and then we'll take constant values of x. So finally we get a number as an integral. So this is geometrically. Let us write down what we mean mathematically, or a formula. So what is written? What written is that
सर ये आपने जो बीच में लाइन बनाई है दोनों कर्व्स के, ये क्या है? ये ग्रीन वाली और
So that is
ऊपर
just a strip. Just to remember that we are integrating along x-axis by the number a to b. So this in the formula this represent double integral x equals to a to x equals to b, y is equals to g1x to y is equals to g2x of the given function dy dx. So this means this. So basically we are taking strip along x-axis. That is the this arrow, upward arrow. And similarly here we have the integral is the constant limit is of y. So y is equals to c to y is equals to d, x equals to h1y, x equals to h2y of the given function dx dy. So here we have taken strip along y-axis. So basically why we are taking constant limit and x we are taking as the function of y. So
Sir, if
depending on what,
the function is not symmetric, then this will not work now.
yeah, so we'll see some example. We will see why we are doing this later on. But let me first write down the statement of the theorem. So after the example, it will be more clear. So let f of xy be continuous function. And if R is defined, so usually we'll take the region bounded by lines or parabola or something. So mostly we'll take the region in that way. So therefore, we will be able to do this most of the time. So if R is the region defined by value of a between value of x is between a and b, value of y is between g1 and g2 curve, where g1 and g2 are continuous. So we need only continuity condition on this curves g1 and g2. So then the integral of r fxy dA, this volume will be written based on this region condition. So that is from a to b, x is from a to b, y is g1x to g2x, fxy dy dx. On the other hand, we have the region which is between x as a bifunction, right? If we have x as a y function, where h1 and h2 are continuous functions, on the interval cd, then we can write this double integral as c to d h1y so this we will call type 2 integral just for the sake of usage, and this we can say type 1. Right, so type 1 means we need to find bound the curve, bound the region in terms of y as a function of x, and type 2 means x as a function of y. So let us see one example. So we want to calculate double integral r sin x by x dA, where r is the region. So we have region is a triangle in the xy plane bounded by x-axis, y is equals to x line, and the third line we have is x equals to 1. So here, first thing what we'll do is we will first find the region. If the region is rectangular, we can apply the Fubini theorem directly and integrate along x or y, right, directly taking the limit if the region is rectangle. But if region is not rectangle, then we need to apply this generalized version, which is a stronger version, and in that case we need to find this curve, either g1 and g2 or h1 and h2. So first thing is to draw in the given example what curve is given, what region is given. So what is the function given here? F of xy. What is f of xy? F of xy is the function which we are integrating, right? So the function which we are integrating is sine x divided by x. So note that here the function of two variable which we are integrating is sine x divided by x. So essentially y is not present in the function, only x is present. So it is like constant function, there is no x present in the constant function. So that means this function is independent of y. So this is the function which we are integrating, and the region is bounded by, in the xy plane, by x-axis x equals to y line and x equals to 1. So let us draw the region first. So in the xy plane, the first line is x-axis. So x-axis we already know, that is already drawn. The second line is x equals to y. That is basically y equals to x. And the third line is x equals to 1. So x equals to 1 means it is a vertical line. So our region is bounded by x equals to 1, y equals to x, and x-axis. That means our region is this one. Right. Now the question is that we have to integrate this with respect to type 2 integral and type 1, because we can't apply the Fubini theorem because the region is not rectangular, it is a triangle, right? So suppose if we apply the Fubini theorem with the second type domain, so for second type we have to take the strip along y-axis, right? So that means for the second type means we have a double integral where we write the function x as a function of y, and then we have a constant limit of y. So if we convert this region in these terms, we have to write this curve that will be our h1x, h1y. So what is the equation of this line x-axis, that is in terms of y?
Y equal to 0.
Y equals to 0, right? And y equals to 0, but I think I have done some mistake in drawing the strip. So let me go back again.
Yes, sir. Horizontal strip will come.
Right, right. So it should be x equals to this to this, that is 4 dx dy. X is a function of y. Yeah, so strip should be in this way. No, no, strip is this one, but that represents this integral as x is a function of y. So now what we are doing is we are taking, so this does not correspond to this integral. So let us simply first bound it as a y as a function of x. So if we draw y as a function of x, this is equation of y is equals to 0, and the above curve y as a function of x is already given, right? So so that is the first integral. So first integral is the integral 0 to 1, and y is from 0 to y is equals to x, and this is nothing but the double integral of the function. So if you integrate the function sin x by x first with respect to y and then with respect to x, so then what we get? So this function is essentially is a function of x. So that means it is constant when we integrate with respect to y. So if we evaluate, we get the limit sin x by x times y, and limit of y is from 0 to y is equals to x. Alright. So first thing what we are doing is y is a function of x, and so what will be the value of this integral? That is x times sin x by x. So now x we can cancel, and this turns out to be integral 0 to 1 sin x dx. So that is minus cosine x. The integral we know that is minus cosine x from 0 to 1. The final answer is 1 minus cosine of 1. So now the next thing is that if we integrate the same area and limit we find x as a function of y, right? Here we have found y as a function of x. So this was basically y is equals to h1x and y is equals to h2x. right? This we don't need to write when we solve the example. Only we write the limit. So now here we have limit of x which is constant. So now how did we found this? Because the region is between x equals to 0 to x equals to 1. So now on the other hand, if we want to find double integral dy dx, then what we need is we need constant limit of y and x is a function of y. So now you tell me what will be the constant limit of y which bounds this region.
0 to 1. Y
0
equal to
to 1.
0 to 1.
Alright, so it's bounded between x-axis and the constant line y equals to d, that is y equals to 1. So that is coming from this point essentially, that is 1 comma 1 point. Right, so that is correct. And then now we need to find two curves which essentially bounds the line x equals to let me use some another color.
X equal to Y.
Exactly. So basically we are finding this curve and this curve.
X equal to 1. Yes, sir.
All right, so that as you said, it is x equals to y from below, because that is the left side curve, and the right side curve is
X
x
equals to
equals to
1.
1. Right, so that is essentially the constant line. So, any doubt in this particular? How did we find this? We essentially use these equations. Okay, so let me evaluate. Let me write down these. So on the other hand, using Fubini's theorem, we get double integral sine x by x dA, which is integral 0 to 1, which is limit of y, integral y to 1, which is limit of x, all right. So that is exactly the limit of x is from y to 1. So now question is that can we find this integral, because we need to integrate this function with respect to x. So this function is does not have antiderivative, right? So note that sin x by x does not have antiderivative. Therefore, we can't evaluate this integral. So on one hand, we can integrate the integral, because what is happening is this formula is helping us to evaluate the given integral, but this formula we can't use. So note that here we can find the limit of the integral for this region in both the cases. But because the function is not does not have antiderivative, using the second method we are not able to find the value of the integral, but we are able to find the integral using the first method. Okay, so let me stop here.